Hey there and welcome to another LeetCode problem. Today we're going to be doing problem of the day for May 26th. It's Stone Game 3, and it's a continuation of the problem we did last time, Stone Game 2. The change in this problem is before you could take m amount of values, right? And then if you took m, then the next person can double what they could take and so on. Where in this problem it's a little bit easier. You can only take 1, 2, or 3 stones instead of piles of stones. This is just stones, but it works the same way where you take a stone and a stone has a value. And so the question asks who will get the highest score assuming Alice and Bob play optimally. And the thing you could recognize in this problem is this is a zero-sum game, right? So if values here are 1, 2, 3, 7, what you can simply do is if you get a score for Alice, right? Let's say Alice has a score of 5. What you can simply do to figure out the score for the other person is you can take the sum. So the sum here would be 13. You can subtract 5 and you would get 8. And so then you can figure out who has the bigger score. So all we really need to do in this problem is, once again, similar to last problem, is we can just calculate Alice's score. And then from there we can get Bob's score by just summing up this whole array. So remember from last problem, and if you didn't watch last problem, I'd encourage you to watch that problem. I'm going to put a link in that video in the description below. And it's pretty much going to be that problem with a little bit of change, so it's pretty straightforward. So in the last problem we discussed how to get Alice's score, right? And the way we did that is we had 3 variables. We had a turn variable, so either 0 or 1. We had an index, which was the index in the array. And then we had m for how many piles we can take, because that changed. But now in this problem, it's actually a little bit simpler, which is kind of funny that this problem is a hard problem while the other problem was a medium problem. I think if you did the other problem, this one is pretty straightforward. So now we just have this turn, and then we have an index. And those are the only 2 values we need. Because all we're going to be doing is we're going to try to take 1 stone, 2 stone, 3 stones, and then we're going to have a visited array as well, right? Because we're going to use dynamic programming just like in the last problem. So we're going to have this visited. It's not going to be a visited array. It's going to be a visited dictionary. And let's just go through what this would look like for Alice and Bob real quick for this one, just like we did in the last one. So let's say we have this 1, 2, 3, 7. And so we pass in an initially index 0, and it's going to be Alice's turn. And so Alice's turn is going to loop through this array, and it's going to try to take 1, 2, or 3 stones. And for Alice, when it's her turn, we're going to try to maximize her output, remember. So we're going to say, we're going to give her some res value, and it's going to be negative infinity to start off. In the previous problem, we had 0, but now we have negative values, so we want to have negative infinity because there are some test cases where all the stones have negative values. So if you have 0, then you'll return 0 for Alice's stones, which should be negative. And then we simply just loop through the total of how many stones we want to take. So let's say we do a max for this. It's either going to be this value or it's going to be the total. So in this case, we take 1 stone plus dp of, and then we're going to do Bob's turn. So let's just say Bob's turn is 1 if Alice is 0, and then we just do the next index. So 1, and then we try 2 piles. So we do the same thing. So we can try to max again with, so 2 piles would be, the total would be 3 plus dp, and it'd still be Bob's turn, index 2, and so on. So that's how we would do Alice. We would just loop through 3 different totals, and we would see which one maximizes Alice's score. And then for Bob's turn, remember, we don't really need to know Bob's score. We can just try to minimize Alice's score. And so for Bob's turn, we're going to make this res value infinity, and we're going to try to minimize it. And for Bob's score, we're still going to calculate Alice's score, but it's going to be on Bob's turn. So let's say, for example, Alice took 1 tile. We're here. Then what we're going to do is we're going to minimize. And so res is going to be min of res, or we don't need the total anymore because we're not adding up Bob's total. So on Bob's turn, Alice's total will not increase. And then we just do dp of, so now it's going to be Alice's turn again, right? So turn's going to be 0, and then depending on how many stones Bob takes, we figure out that index. So let's say Bob takes this stone, Alice is going to be over here. So that's going to be 2, and then if Bob takes both of these stones, then it's going to be 3, and so on. So we're just going to try to minimize Alice's dp on Bob's turn, and we're going to try to maximize Alice's DP on Alice's turn. And that way we're going to get a total for Alice. And once we get a total for Alice, we can get a total for Bob by simply doing the sum of these values minus the total for Alice. And then all we have to do is just see which one has the bigger number, and that one wins. So for this problem, the optimal solution would be, well, there's only 4, and Alice can take 1 through 3. So if Alice took 1, Bob would take 3, and so on. So the optimal solution is Alice would take these, and then Bob would be over here, and he would take this one, and Alice would have 6, Bob would have 7, so Bob would win. And then for the second example, same thing. Alice would take the first 3, Bob would take this. And then Alice would win because Alice would be at 6 and Bob would be at -9. So that's kind of how we're going to do this. And if you're still a little bit confused, like I said, I'd encourage you to watch the earlier video because I went into detail on that. And the code is going to be very similar to the last, to the Stone Game 2. Okay, so let's try to code that up. So first of all, remember we're going to have a visited. So we're going to have a visited dictionary. And we're going to have the same def DP thing. Now, like I said, we don't have an M value that we had in the previous problem, so that's going to be a little bit simpler. So all we have is a turn and an index. Okay. And what's our base case? Well, our base case is we're actually out of bounds, right? If we're out of bounds, then the score we return is 0. So if index is greater than or equal to stone value, we're going to return 0 there. And then the other base case, as usual for memoization, is just going to be if it's in our visited hash map, then we can return that, right? So if turn index in visited, return visited turn index. So that's straightforward. Now, what we need to do is figure out what we're going to initialize our res to, remember, if it's Alice's or Bob's turn. So let's say Alice's turn is 0. I don't remember what I made in the last one, but we'll just say Alice's turn is 0 and Bob's turn is 1. So let's write that down. Alice's turn is 0, turn is 1. So if turn equals 0, then we're going to make, remember, we're going to make res negative infinity, and we're going to try to maximize it. So and we're going to try to maximize it. Otherwise, we're going to make res infinity, and we're going to minimize it. Okay. Now we need this total variable just like last time, so we're going to have, or we call that stones, I believe. So, and what we're going to do is we don't actually need it now because it's a little bit simpler, but before we were going through an array and we were getting a ton of values, but we can still use it here, so that's totally fine. So then we just loop for I in range. So the most stones we can pick up is 3, so we're going to loop through 3. We're going to do stones. Oh, and then we also have to check, just like last time before we're out of bounds, right? Let's say we're on this index, and we try to pick up 1 stone, okay, 2 stones, okay, and then we try to pick up a 3rd stone, we're out of bounds. So we do need to make sure that we're not out of bounds. If we're out of bounds, we can just break this loop, because we can't pick up any more stones. So then we would just say if index plus I equals length of stone value, you can break here. Although technically, I think what it would do is it would still work because it would try to calculate something and then it would go up here and it would break there. But whatever, it's fine. Okay, so now remember we need to have our two cases: if it's Alice's turn or if it's Bob's turn again. So same thing. So if turn equals 0, which means Alice. Res equals, we're maximizing here, so we're picking up some stones, or sorry, so it's going to be our old res. We're going to pick up some stones, which is our current total, right? So like, let's say we started here, stones would be this, then we go to the next pile, stones would keep adding the pile we're adding. So like here it would be 1, here it would be 3, here it would be 6, and that's how many we pick up in this current iteration. Then dp of wherever we go next, right? And wherever we went next is index plus I plus 1. Right, so if I is 0 through 2, and we're on here, let's say I would be 0, and we need to go to this value. So that would be index plus I plus 1, and so on. This is index plus I, we need to go to the next value. Okay, so that's going to be index plus I plus 1, and then for the turns first, actually, in this case. That's fine. So for turn, we can just do turn I don't remember what I did in the last one, but we can do something like this. We can XOR turn with 1. So 0 XOR with 1 is 1, and 1 XOR with 1 is 0. Exclusive OR means only one of the ones can be 1. You can also do something simpler, like if 0, then 1, if 1, then 0, whatever you like. That doesn't matter too much. Okay, so that is that. Now we need to minimize for Bob. So we minimize. Remember for Bob, on Bob's turn, Alice doesn't get any stones, so we don't need to add the stones. We just minimize the DP of when it's Alice's turn. So same thing. 1 index plus I plus 1. Okay. Now we need to put that into our hash map. Okay, so now what we're going to get is we're going to get an Alice's score. So just call it Alice score, or Alice. That's going to be DP of Alice is going to be turn 0, remember 0. So this is Alice's score, because this is what we're doing in this top-down dynamic program. We're getting Alice's score. Now to get Bob, we need to get sum of stone value minus Alice, right? Because it's a zero-sum game. Then, pretty straightforward, we just check. So if Alice is greater than Bob, return Alice. If Bob is greater than Alice, return Bob. Otherwise, they're equal, so we just return tie, right? Okay, so let's try that. Okay, and we screwed something up here, so let's see. Okay, so let's actually print Alice just to make sure we're doing everything correctly here. So okay, so we're printing 0. So let's figure out, we must have screwed something up here. So let's see what we did. Oh, if index less than stone value, that's fine. That's fine. That's fine. Right, so what we missed is we forgot to add our stones. So this is always 0, so stones plus equals stone value index plus I. Let's see that. Okay. We might have a, can get rid of that, but. Okay, so it looks good. So it's pretty straightforward, and like I said, if you can do some game 2, this is really straightforward. You just change a little bit of code, and it's pretty much done. So now let's think about the time complexity, and this is going to be a lot smaller time complexity and space complexity than our old one. So for time, we have an index, which is going to be big O of n, and we have a turn, which is only going to be 0, 1. So our time is going to be 2 times index, right? Which is just index. So if index is n, that's just big O of n, because that's all we're doing is because we're caching, we're only going to be on each index twice, for a 0 and for a 1. So that's big O of n. And for space, we are storing the same thing. We're storing this visited hash map for every single case, and that's going to be big O of 2 times n, which is big O of n. Okay, so that's all for this problem, and I hope you liked it. And if you do, please like and subscribe. It supports the channel, and I'll see you in the next video. Thanks for watching.